Hey everybody, and welcome to Algo Expert. In this video, we will be going over the merging linked lists question. So in this question, we have two different linked lists. So we have linked list 1 and linked list 2. But these two lists converge where they intersect at a single node somewhere in the middle. So they share some portion of the list. So for example, linked list 1 starts with this node 2, and then we have the node 3, and then we have this node 8, and then the node 4. Linked list 2 starts here with 6, the next node is going to be the same 8, and then the next node is that same 4. And the goal of this problem is simply to return whatever node is the intersection point, so where the two linked lists merge. So in this case, we would return this node 8. And it's important to note that we are not just returning the number 8, so we do not return the value, but rather we return the shared node. So we would return this entire node, which of course still has its next pointer to the 4 as well. So in essence, we are returning a linked list that is all of these shared nodes. Additionally, if the two lists do not intersect, then we just return null or none. Okay, so there's a few different ways that we can go about solving this problem. But the first thing that's important to notice is that once we get to the intersection point, so once we get to this 8, all of the nodes after that in both lists will be exactly the same. So we have the 8, and then we have the 4, and these are shared between both lists. And conversely, we also know that any node before the intersection point is not a shared node. So the 2 and 3 are not shared nodes, and neither is the 6. So we can use this to come up with our first solution. Essentially, what we want to do is we want to iterate through these lists and just check until we find a node that is shared. So the way we can do this is we can just choose one of the two lists to iterate through, and we can create a set of all of the nodes that are in that list. And then we can iterate through the other list, and as we go, we can check to see if any of the nodes are in the first list. And we would of course check that using that set. And whenever we find a node that is in the first list, that must be the intersection point because it would be the first node that is shared between them, and we know the first shared node is the intersection point. Okay, so let's walk through this solution. So we can create a set. I'll call this list 1 nodes, and we will set this equal to initially an empty set. And now we're just going to iterate through list 1. So we will start at this first element, which is the 2, and we can add that to the set. And again, we would not just be adding the values, but rather we need to add the entire node. So this 2 here is not just the number 2, it represents this entire node. Okay, so now we would move the current pointer to the next node. So we would move it here. Now we are at this 3, and we can add the 3 to the set as well. And then we can simply continue. So the next node is now the 8. So we will add the 8 to the set. And then we continue again, we have this 4, so we can add the 4 to the set, and 4 does not have a next value, so now we are at the end of list 1, so we are done adding nodes to our set. And now what we want to do is we want to iterate through linked list 2, and we want to find the first shared node. And the first shared node is going to be the first node we encounter that is in list 1 nodes. So in our set of nodes we found before. So to begin, we can put a current pointer on the first node of list 2. And now we check, is this node in list 1 nodes? And it is not. So what that means is we just need to continue. So we can move on to the next node. And now we have this 8, and we can check list 1 nodes, and it turns out that the 8 is in list 1 nodes. So that means we must have found the intersection point because this is the first node we have encountered that is shared, so we can simply return this 8. And then of course, if we did manage to get to the end of list 2 without finding a shared node, we would just return null or none. So if the lists do not intersect, we just return null or none. Okay, so that's going to do it for the first solution. So time complexity wise, this is going to run in big O of n plus m time, where n is going to be the length of list 1 and m will be the length of list 2. And the reason for this time complexity is simply because we have to iterate through both of the lists. This will also take big O of n space, again, where n is the length of the first list. And the reason for this is because we have this extra space for list 1 nodes. So we add all of the nodes from list 1 to this set. So because of this, we have O of n space, but we never add list 2 nodes to the set, so we do not use any space for list 2. Okay, so this solution works, but let's see if we can try to improve it to not need this extra space for the list 1 nodes set. So I'm going to remove all of our markings here, and I want to again approach this problem in the same way, but see if we can do it without needing the extra set. So the key idea here is going to be that rather than using a set, we can calculate where the intersection point is based on the lengths of these 2 lists. And the reason this is going to work is because we know from the intersection point on, the lists have the exact same length. And we can also get the entire length of a given list. So for example, this list has a length of 4, which we can get simply by iterating through the list and adding 1 with each iteration. We also can figure out that list 2 has a length of 3. So we know that list 1 has this length of 4. And then we know list 2 has a length of 3. And the difference between these 2 lengths is 1. So that means that list 1 has 1 more node than list 2. And we know that after the intersection point, all of the nodes are the same. So we know at this point on, the nodes must be the same. So that means the extra node must be at the beginning. So essentially what we can do is we can iterate through the 2 lists again. So we can start from the 2 for list 1, and we would start from the 6 for list 2. But again, we know that there's a difference of 1 in the lengths of the list. So this has a length of 4, and this has a length of 3. And we want to get to this intersection node at the exact same time. So the way we can do this is by first iterating through list 1 because it is the larger of the 2 lists, and we will iterate until we get to the point where the remaining lists are of the same length. So to do that, we would simply take our list 1 current pointer, and we would move it to the next node. And again, the difference in length between these 2 lists is 4 minus 3, so it's only 1, so we only need to do 1 iteration, and now the remaining lists are of the same length. So what that means is if we now increment at the same time, we will get to the intersection point at the same time. So we can increment list node 1 first of all, which would go to the 8, and then we would also increment list node 2, which would also go to the 8. And now we simply do a check to say, are both of these current pointers pointing to the same node? And they are, which must mean we got to the intersection point, so we can simply return 8. And again, this would work no matter how large the linked lists are and where the intersection point is, because we iterated in one of the lists first to get them to the same length. And once the 2 lists are of the same length, we know that we will reach the intersection point at the exact same time. And then again, if we get to the end of the lists without ever finding an intersection point, we would return null or none. Okay, so this is once again going to run in big O of n plus m time, where n and m are once again the lengths of list 1 and list 2, and this is again because we have to iterate through both of the lists. But then for the space complexity, this will be big O of 1 space, because we are not using any extra space that will scale with the size of the input. Okay, so now let's erase this one more time, and I do want to show one more solution that we could use to solve this problem. So for this solution, we are going to use the same information that we learned about the lists before, but we are just going to use it in a slightly different way. So let's start by creating a current pointer to iterate through both of the lists. So we can start at the 2 here, and then we will start at the 6 here. So now let's just see what would happen if we just start iterating through both of the lists. Well, if we iterate first of all with list 1, this would go to the 3, and then with list 2, this would move to the 8, which of course is the intersection point. But then if we just continue, the list 1 current pointer would move to the 8, and the list 2 current pointer would move to the 4. So now if we continue even further, the list 1 current pointer would move to the 4, but now the list 2 current pointer is already at the end. So where does it go now? We want to get to the 8 at the same time with both pointers. So how can we do this? Well, to do that, what we can do is we can move the list2 current pointer to the beginning of list1. So why are we doing this? Well, we are doing this because we want the total number of nodes that both pointers went through before getting to the intersection point to be the same. And the way we do that is by having both pointers go through both lists. So now in the next iteration, the list1 current pointer will move to the beginning of list2. And the list2 current pointer, which is now in list1, is going to move to its next node as well, which is this 3. And now in the next iteration, the list1 current pointer, which is currently at the head of list2, is moving to the next node, and the same is true for the other current pointer. So this one is going to move to the next node, and now they are both at the 8, which is going to be our intersection point, and because both pointers are at the same node, we would return that node, which again is the node we want to be returning. And again, this works for the same reason as our counting solution. It is just a slightly more clever way to approach using the intuition from that solution. So because we have the same number of nodes at the intersection point and beyond, and because we might have different number of nodes before the intersection point, essentially what we do by wrapping our pointers around to the other list once they get to the end of the initial list is we make sure that they go through the same total number of nodes, and then they essentially end up aligned with each other, and they will meet at that intersection point. So just like the previous solutions, this one is going to take big O of n plus m time, again, where n and m are the length of the two different lists. And again, we will be using big O of 1 space, so only constant space because we are not using any space that scales with the size of the input. And with that, that will complete the conceptual overview of this problem. Now let's move over to the code editor for a code walkthrough. Okay, so now we are here in the code editor, and we have our merging linked lists function, and it takes in linked list 1 and linked list 2. And let's start by implementing the first solution, and that was the solution using the set. So we want to first get a set of all of the nodes in linked list 1. So let's say list 1 nodes, and this is going to be equal to a new set. And now we need a current pointer so that we can iterate through list 1. So we can say current node 1 is going to be equal to linked list 1. So we start at the head node, and then we are just going to iterate until we get to the end. So we can say while current node 1 is not none. So while we still have a node, what we want to do is first of all add that node to our set. So we can say list1 nodes.add the current node 1, and then we want to move the pointer. So we can say current node 1 equals current node 1.next. And now we should have added all of our list1 nodes to the list1 nodes set, and now we just need to iterate through the list2 to see if we find any of these nodes. And if we do, we can return the first one that we find. So let's come down here, and we can say current node 2 to iterate through linked list 2 is going to be equal to linked list 2. And once again, we can have a while loop. So while current node 2 is not none, so while we still have a current node 2, what we want to do is we want to check if current node 2 is in the set. So if current node 2 is in list 1 nodes, so if it is in those nodes, then this must be the intersection point, so we can return current node 2. Otherwise, we just keep iterating, so we can say current node 2 equals current node 2.next. And now if we get to the end of list 2 and we never found an intersection point, so we never found a node that was in list 1 nodes, then we simply return none because there is no intersection point. And now again, this is going to run in big O of n plus m time, as well as big O of n space. And again, the n plus m time is because we iterate through both linked list 1 and linked list 2, and the O of n space is the space we use for list 1 nodes. Okay, so that should do it for the first solution. So I'm going to go ahead and comment all of this out, and then we can make some space below here for a second solution. So for the second solution, let's first of all add the function declaration. So we can say we have the function merge linked lists, and this takes in linked list 1 as well as linked list 2. And now for this solution, what we want to do is we want to get the length of both of the lists. So essentially, we are just going to count all of the nodes in list 1 and in list 2. So again, we need a current pointer, so we can say current node 1 is going to be equal to linked list 1, and then we can also set an initial count, so we can say count 1 is going to be 0. And now we just need to iterate through linked list 1 and increment the count for each node. So we can say while current node 1 is not none, we are going to increment count 1, so count 1 plus equals 1, and then we can move current node 1. So current node 1 equals current node 1 dot next. And next we just do the same thing but for list 2 to get the length of list 2. So we can say current node 2 is going to be equal to linked list 2, and then count 2 is going to be equal to 0 as well. And while current node 2 is not none, we are going to increment count 2, so count 2 plus equals 1, and we are going to update current node 2 to be current node 2 dot next. Okay, so now I'm going to scroll down a bit to give us some more space. And next what we want to do is we want to get the difference in the two counts, and we also need to figure out which of the lists is the bigger list. So first of all, the difference is going to be equal to the absolute value of count 2 minus count 1. And then we need to get our two current pointers, but know which one is the bigger list or the smaller list. So we can start with the bigger current node, and this is going to be equal to linked list 1 if count 1 is greater than count 2, otherwise it's going to be equal to linked list 2. And then we can do essentially the same thing for the smaller current node. So we can say smaller current node is going to be equal to linked list 2 if count 1 is greater than count 2, otherwise it will be linked list 1. And now we just want to iterate with the bigger current node until we have the same length. So we want to iterate difference times. So we can use a for loop for that. So for in range, and we just want our range to be the difference. So we want to iterate difference number of times. And for this, we just want to move bigger current node to bigger current node dot next. And now if we start from where bigger current node and smaller current nodes currently are, the length of those lists should be the same, and thus they should hit the intersection point at the same time. So we can say while bigger current node is not smaller current node, so while these are not the exact same node, we will just move both of the pointers. So we can say bigger current node equals bigger current node dot next, and smaller current node equals smaller current node dot next. And now when we finish the while loop, they are going to both be the same. So in that case, we can just return either of the values. So I will say return the bigger current node. It's also worth noting that if there is no intersection point, then we would get out of the while loop when both of these values are none, because they would then be the same. And in that case, we would return either one, which would be none. So we would return none as we expect. And once again, this function is going to run in big O of n plus m time, as well as big O of 1 space, because we are not using any extra space, but we do have big O of n plus m once again, because we are still iterating through both of the lists. So we iterate through both of them here to get the counts, and then again, we iterate through at max both of them completely once again. So we do 2 iterations, but it is still big O of n plus m. Okay, so that's going to do it for the second solution. So I will comment this one out as well. And we can come down below here and we can start implementing the third solution. So let's once again add the function. So merge linked lists, and this will take in list 1 as well as linked list 2. And now for this solution, we just iterate through both lists at the same time. And if we reach the end of one list, we just move the pointer to the other list. So first of all, we can have current node 1 is going to be equal to linked list 1, and current node 2 is going to be equal to linked list 2. And the while condition this time will just be when these are not equal, we want to continue. So while current node 1 is not current node 2, we want to continue iterating. So first of all, we need to update current node 1. So we either move it one forward, or if we are at the end of the list, then we want to move it to the beginning of list 2. So if not current node 1, then what we want to do is we want to say current node 1 equals linked list 2. So that is going to move it to the beginning of list 2 if we are at the end of list 1. Otherwise, what we want to do is we simply want to update current node 1 just like we have before. So current node 1 equals current node 1 dot next. And then we can do the same thing for current node 2. So if not current node 2, then what we want to do is set current node 2 to be equal to linked list 1. Otherwise, we will just update current node 2 to be the next node in the list. So current node 2 equals current node 2 dot next. And then once we get out of the while loop, all we need to do is return either of the nodes. So we can return current node 1. And again, the nodes must be the same to get out of the while loop, so it does not matter which one we return. And this would also work for the case if the lists never merge. And the reason for that is that when we get out of the while loop, in that case, both of the values would be null or none, so we would just return that value as we expect. Okay, so now this function is again going to be big O of n plus m time, as well as big O of 1 space. And this is essentially for the same reason as the previous function. So big O of n plus m time, because we do iterate through both of the lists. It might seem like one iteration here, but because we move the current pointer to the head of the other list once we finish the first iteration, each current pointer could go through the entirety of both lists. And then again, we have big O of 1 space because we do not use any extra space that scales with the size of the input. And with that, that is going to be the end of this video. I hope you found it helpful, and I'll see you in the next one.